But anyway, my name is Yukinori Ohta from Chiba University, Japan, and my title of my talk is the theoretical perspective on Excitonic insulator, tantalum to nickel selenium 5. Oh, really? Okay.
Yeah, you can. Okay.
Thank you. And I'd like to thank the organizers for inviting me to this nice workshop. And okay, my collaborators, Ohta Sugimoto now in Keio University, and Satoshi Nishimoto, TU Dresden, IFW Dresden, and Tatsuya Kaneko, now Columbia University, and Professor Millis' group. And also, I would like to thank this experimentalist group, in particular, Professor Sawa, previous talk. And I will begin with some small introduction, and also I will give you some theoretical aspects of this material, and I would like to make some perspectives based on the optical conductivity analysis. Dr. Boris already mentioned, but here also I would like to discuss some aspects. And I would like to suggest a normal insulator state. A summary will be given. And this work is already published in this paper. The external condensation, as you know, occurs in either small band gap, this is a band gap semiconductors, or small band over semimetals. Here, the semimetallic region. And the condensation occurs in semimetallic systems. The condensation occurs in analogy with the BCO theory of superconductivity. And in semiconducting region, you have the BEC type external condensation. And this is the band structure. Above TC, semimetric region, you have the semimetal, and below TC, you have the small band gap. And the semiconducting region, you have the band gap, and below TC, you have the flattening of the valence band. Okay, and this is a schematic picture of excitons. And because okay, and tantalum to nickel selenium 5 should be in the BC regime, because we understand that this should be the case in this system, because this system is insulating in the temperature, entire temperature range of Earth. Very high temperatures, it's rather a small band gap, but almost entirely it is insulating. So that we are here in this region. This is the standard understanding. But what I would like to show here is that this conventional understanding is in fact seriously violated in this tantalum to nickel selenium 5. Okay, this is what I want to show in this talk. Okay. Okay, this is a crystal structure. You have the layer structure and nickel red balls here running along the A direction, and we have two tantalum chains. So 3-chain structure is a basic unit of this material. The transition, structural phase transition occurs at 328 Kelvin from the orthorhombic phase to the monoclinic phase. The monoclinic angle, change in the monoclinic angle is very small, so that this picture is very much exaggerated. Okay? And no seasonal modulation, but that is uniform lattice distortion. And insulating the entire phase diagram, entire temperature range, so that Felix seems to be relevant. And our issue is what is the origin of this structural phase transition. Okay? And this is the band structure calculation of this material. Using Win2K code, using GGA approximation. Such calculation, as you know, the band gap is underestimated. So we have a semi-metallic situation in the standard calculations. But in this case, we introduce orbital-dependent side potentials to open the band gap. And we found that there is a nickel 2 bands and tantalum 4 bands. It's the same thing, weight plot, just weight plot. And we have two sets of 3 chains, so that we have 2 bands and 4 bands. 2 bands nickel chains and 4 bands tantalum chain. Okay, and from that calculation, we make the model. This is the template model. We have nickel chain and 2 tantalum chains, and we have 2 non-degenerate F band. This is nickel. And doubly degenerate conduction band, because we have two chains. And we also we introduce Hubbard-like model, on-site Coulomb interaction and inter-site Coulomb interaction. And also the structural phase transition should be explained. So we introduce the 4 degrees of freedom. And we make a mean field analysis. So this model and found that the excitonic bond order formation is what occurs in this system. Okay? So exciton is formed between nickel 3d hole and a tantalum 5d electrons. So this is the exciton. And this bond order formation is the origin of the structural phase transition. Okay? And as you see this figure, an Alpes measurement, we have the flat band, and even above TC has a flat band. And the double peak structure seems to be appearing here, double peak. And this is a finite temperature variational cluster approximation calculation where the electron correlation is taken into account for a simple model. And we found that the double peak structure and also above TC, we have a flat band. Yeah. Okay. And we have calculated other physical quantities of this material, including specific heat for the phase transition and shear constant for the lattice distortion and quantum interference effect, including NMR relaxation rate and ultrasonic attenuation rate. And also diamagnetic susceptibility has been calculated. And the agreement seems to be somehow reasonable. So I should say that so far so good. And recently, a comparative study of the optical conductivity between the selenium system and sulfur system. This is Dr. Boris showed. And this panel is the selenium system, and these panels are for the sulfur system, 10 Kelvin data. Okay, this is the optical conductivity along A-axis, electric field along A-axis. So A is the change direction, and C is perpendicular to the change direction, and B is perpendicular to the plane, and so that there is no experimental data here, theoretical curves. And this peak is quite enormous. Okay, this one, and this is a temperature dependent. This peak, and this peak is absent. I think this very important peak is absent in the sulfur system. And this is temperature dependence. We have the 150 Kelvin, this peak. And red curve is just at the transition point, and 350 Kelvin. So even above TC, you have a peak. So the peak appears below, both below and above TC. This from this papers. Okay. And we want to explain this structure features, and we made the band structure calculation again. This is for in this case we use modified Becker-Johnson BMJ.
The previous calculation, the previous results are consistent with Boris' results. You were saying that the peak that doesn't show up, okay, that is present above and below TC. But okay.
Sorry?
No, that one. The anomalous.
This one?
Yes.
Where? This one. Yeah, this is from this.
Right, this, okay.
Okay, this is.
Okay, sorry, I didn't see that.
Okay. And we made the band structure calculation in this case. And this is modified Becker-Johnson type exchange potential. And this method, we can improve the underestimation of the band gap so that we have a band gap here for selenium sulfur system. And this is experimental photo emission data, and they are consistent. So sulfur system is a semiconductor, I think. But in the selenium system, this method with C value 1/5, this I think it's a standard value for semiconductors. And in this case, we have a semi-metallic band value. So this experiment is insulating, so that this insulator is somehow strange insulator. Okay, so we want to discuss the origin of this.
I'm sorry. If you go back one slide, those are experimental data of ARPES taken on the selenium and the sulfide compounds, right? These are unpublished.
Yeah, maybe they are unpublished.
They are unpublished.
This one is published.
That's published, but the sulfide is not published. No. So there's another work on the sulfide in another journal, but it's not that one. Okay.
And this is the calculated optical conductivity. this is the theory result, and these are the corresponding experimental result. And electric field parallel to the A direction, we found these peaks. We have peaks. Okay, let me see. It's perpendicular to the chain electric field. So we have alpha peak here, beta shoulder is here, and gamma peak is around 3 electron volts. We have peak here, and delta peak is here. And also we have alpha peak, beta peak, and gamma peak, delta. And they are very much in agreement with experimental theory agrees very well. And also, electric field parallel to the chain direction, alpha peak, beta peak, and gamma peak, and delta peak. And they also appear in this phase system. And so we can say that above 1 eV photon energy, the agreement between theory and experience is very good. What do you think? And the issue is that this one, there is no corresponding peak. Instead, you have to drill the peak because this is semi-metallic situation. Okay? So what is the origin of this peak? It should be explained. And we made this peak. And we made a simplified model calculation for this, for using this model. This is thinness model, nickel F band, two-chain model, nickel F band and tantalum C band. And the level separation is D. And we introduce the interside Coulomb interaction. And we make use of the dynamical density matrix normalization method. And we obtain this sigma of omega, optical conductivity, and think about the excitation spectrum. Okay, and with increasing V values, we have a peak here. So this, and I think this peak can be explained by this peak. Okay? And also we have to think about the gap, so that the system is insulated, which is consistent with the experiment. Okay? And simplest interpretation is that assume a semi-metallic situation. We have the holes in the valence band and electrons in the conduction band. And if you apply electric field, this electron hops from here to here, so that the system gains energy V. So this peak corresponds to this peak. And also we have the hole hop from here to here, so that the energy increases by V. So this is the most simplest understanding of the origin of the peak. Okay, and also we have the electron repulsive interaction, or that means that electron-hole attractive interaction, so that we have a band gap here. Okay, this is so. Okay, at least in the strong coupling regime, we have the peak in sigma over omega at V, and band gap opens of the size V. The band gap of the size V opens. So V is the important thing, and V is nothing but the electron-hole attractive interaction, but the exciton formation energy, basically. Okay. Okay.
So I didn't get exactly that. V here is a hybridization matrix element?
No,
is an interaction?
No, interaction. And I also should say that only upspin electrons are drawn here, because we are, this model is a spinless model. Okay, so upspin is taken down.
So this is the same as the Falikov-Kimball model?
That's right, that's right. Okay. And to envisage the exchange phases, more clearly, we draw the ground state phase diagram. This is a two-band Hubbard model, and this is a two-chain Hubbard model, and this is for the three-chain Hubbard model. In semiconducting region, have the band gap, and if interaction strength V over T is hopping, V is interaction, is strong, then we have the VC type exchange condensation. But when V is small, and in the semi-metallic region, we have the VCS type condensation. Okay, this is the standard. But in the three-chain model, we have a semiconducting region here, and uniform excitonic insulator state here. But in a weak coupling region, V is small, we have a fluid level lacking of excitonic type excitonic condensation. This is a finite, excitons have finite momentum, okay? And this is the theory result of this paper. So we put it here. Okay, this is the Mayfield calculation again. Okay, and this is also this is standard temperature band gap phase diagram, and the 3K model has a FFLO type exchange phase here, and so in our tantalum to nickel selenium 5, maybe located around here in this, if we assume the V interaction is weak enough. However, I think that in reality, we are located here, semi-metallic region. The band gap is negative, but the interaction strength is strong enough. So this is the excitonic insulator state of the BEC type. And above TC is a state of preformed excitons with a band gap and peak in the optical conductivity spectrum. So this is the simplest understanding, I think. And this is a pure 1D calculation, one-dimensional calculation, so that we have excitonic phase in a very low interaction strength. But if the nesting is not perfect in 2D, we have the paramagnetic metallic phase, semi-metallic phase around here. Okay. So I just want to say this is a noble insulator state. And this noble insulator state is caused by the strong electron-hole attractive interaction. And this may be contrasted with the multi-insulator state.
To be precise, because it's good to say there is a strong electron-hole attraction. How do you know there is a strong electron-hole attraction, besides that you put it in the model?
That is very simple. I mean, only repulsive interaction is introduced in the model. V is repulsive interaction between electron and electron. Okay? But the repulsive interaction between electrons, if you electrons shift from here, this one action and the hole here gives you attractive interaction.
Yeah, but this basically you're putting an attractive interaction which is electron hole and a screen.
No. Oh, you only include the repulsive interaction.
Eh?
We only include the repulsive interaction, V, and I just interpret the effect of electron repulsive interaction. That is nothing but the electron-hole attractive interaction. Okay.
But this again, I keep saying that you are assuming that all interactions are unscreened.
Unscreened interaction.
Yeah, that this makes no sense in a real material.
I don't understand.
I mean, electron and electron-hole interaction are screened by the rest of the electrons. What I'm trying to say is that in order to reach this Bose-Einstein
I mean, this is purely a model calculation. We only have the electrons here, and in this case, we have the electron repulsive interaction. But this is, in this sense, in this model, if you put, okay, this electron cannot. It's hard to shift from here to here because we have a repulsive interaction. That means that this electron wants to have a hole here. So this is the electron-hole pair. You see? So electron repulsive.
No, but this I perfectly understand. What I'm trying to say is that the parameters that you put in the model, they have to be consistent in whatever correlated system with the screening you have in the material. And then basically what the values that you are putting is an unscreened Coulomb interaction in an otherwise screened system, which is highly screened because it's either semi-metallic or metallic.
Okay. Yeah.
Then basically there is a second thing that basically you decide to kill the screening.
Okay. Yeah. This is order, and we do not include screening effect.
Exactly, because in the past.
Okay. That is the model. And, within this model, we want to understand. I think this is the how should I say? I think this is the rule of the game. This is a strongly correlated electron model. We do not include the screening effect by hand. That is, I think, it's a standard way of considering the things, in my opinion. Okay. Anyway. Okay. Anyway, okay. Yeah. So maybe you can say that noble insulator state caused by strong electron repulsion. That is nothing. That I can say. And also, the multi-insulator state is caused by the electron repulsion. That's okay. So they are very similar things. Okay. And our theoretical prediction is that non-integrated band structure is semi-metallic. This dashed curves. and strong electron-hole attraction or electron-electron repulsion, we have this solid curve. We have the gap, and the real space pairing, and the bond order formation is what occurs in this system. And there is a peak in the optical conductivity, and band gap opens, and above TC it is the state of preformed pairs. And the experimental evidence is that the semiconductor in the entire temperature range observed, and large peak in sigma over omega at 0.4 electron volt, and that peak structure in the output measurement are this one. That peak. Okay, and okay, again, I want to stress these things. Noble insulator state occurs in systems of even number of electrons per site, and this is insulating without excitonic condensation, even above TC. And also, we have the multi-insulator state. Multi-insulator state occurs in systems of odd number of electrons per site, as you know, and even above TC, it is insulating without magnetic order. And if we decrease the interaction strength, then we have the metallic state. Okay, and this metallic state can be realized in this interesting experiment. This material, and this is made by Okazaki at ISSP, University of Tokyo, published in this paper. And this is time resolved the angle resolved total emission spectroscopy, pump probe experiment. And before pumping, we have the flat band here, and just after pumping, we have the spectral weight near the Fermi, around the Fermi level. And this one, here, spectral weight increases. Here, red region. And here, you make RPS measurement, then this is the band structure of this phase. So we have a semi-metallic band dispersion here. And simplest interpretation would be that...
Sorry for interrupting you. How can it be 30 microjoule per centimeter squared? That's a very low fluence for an RPS experiment.
Really?
The number is...
This one?
Yeah, it's quite strange.
Really? I do not really understand.
Okay.
This one is 1 point. This is the data from paper. So I think I do not write this. So I don't know. This is small or not. Okay?
But this is not consistent with
yeah. The result is not consistent with more result. So this is interesting. But anyway, this is interesting. And what is the difference between these two experiments, Moore-san and Okazaki-san? I asked Okazaki-san, and he explained to me like something like something, but I do not understand. And also I asked Moore-san, and she said, I don't know. Anyway, so this is what occurred in this experiment. We have the non-interactive band dispersion, which is semi-metallic. And hot excitation free carriers screen the Coulomb interaction, then we could virtually observe this non-interactive band dispersion. This is another interpretation, I think. Okay, this phase diagram, we have the excitonic insulator say somewhere here, and photo excitation shifts this peak position to here, down here, semi-metallic. And in the 3-10 models, the same thing. Okay. Okay, let me summarize. Density function theory calculations of optical conductivity explain high energy spectral features very well. But for low energies, we found that while sulfur system is a simple semiconductor, selenium system is a band of about 10 meters, even in the MBJ type of calculation. And the effective model calculation for tantalum selenium-5 showed that the large peak appears in sigma over omega, and the band gap opens in the sigma-particle spectral function, both of which are due to the strong electron-electron correlation effect. Okay, and the ground state of tantalum to nickel selenium-5 is an excitonic insulator of the BEC type, despite the fact that the non-interactive band dispersion is a band over a centimeter. So this is different from the conventional understanding, I think. And also, noble insulator state is thus caused by the strong electron-hole attraction, and I think is predicted, and which may be contrasted with the multi-insulator state caused by the electron-repulsive interaction. Okay, this is Thank you very much.
Okay. Something for discussion. I will just make one comment and not this. I'm happy with most of the things you put, but I think this sentence, number 5, is wrong. No, number 4.
Number 4.
Number 4.
So maybe we can at least open it for discussion.
And now we discuss.
This, sorry.
No. Questions?
Okay.
And then,
Well, I have a question when you show the optical conductivity and the peaks alpha, beta, gamma, delta. So how the position of these peaks depend on this parameter C that you choose?
If you
You choose C to fit the peaks, or it's rather independent of?
this, if you increase this value, the peak shifts to higher side.
Okay, so this value is picked up in order to match the peak.
But I think this 1.5 is not too large. It's a standard.
I'm not an expert, but when I see this thing,
And but only this value, assumption is this value. And we are very...
And you need to make the same assumption for both materials.
That's right.
You had this one slide where you had your theoretical predictions and then experimental evidences, and then there was, I think, your point 5 was this preformed pairs above TC. So what would be then, because I think that was now somehow, I had the feeling that was one of the concluding things, that somehow this high temperature phase is,
We don't
comment on this.
We don't make any calculation for that at the moment. Yeah, and actually now we are calculating the finite temperature phase diagram, including the spectral function, finite temperature spectral function. And we obtained already a preliminary result. And I think it's not too wrong. I think it's not too wrong.
No, but broadening a bit the question of Stefan, I think this is the same question that Anne has, right? I mean, to what extent can we converge on a picture which is there in this system BC condensation of exciton, or should we think of it as the high temperature phase has no excitons, and then there's a symmetry breaking into a phase that has excitons? So my own, but this is my own personal view, is that many of the things we've seen today, including theory and experiments, suggest that there are no excitons in the high temperature phase, and we have a low temperature phase which has an excitonic character, but doesn't have, but we can't talk about an excitonic condensation. So I have to say, I don't understand the statement that the high temperature phase is a semi-metal, but at the same time they are preformed quote-unquote pairs. What does that mean? I'm lost here.
Okay, the only thing, the problem is that we do not have, the non-interacting band dispersion, non-interactive band dispersion is an assumption. We do not observe basically this one, non-interacting band. This is a hypothetical concept, okay? But if we assume that the band structure is semi-metallic, then interaction gives you this insulating state, BC type exchange condensation. Assumption here. If we assume this one, then we have this, we can explain many things. For example, For example, these things, double peak structure, peak in the sigma omega, and semiconducting in the temperature range of that. Also, this one. This one. I saw this experiment for the first time. This should be the screening effect. I mean, the photoexcitation free carrier gives you this band dispersion.
Can you comment about the little spectral weight that is seen in the transient Harper snapshots above the Fermi energy before pumping? So if I look at the snapshot, so on your right,
what?
Right?
Right?
Yeah, over there, yeah. What's the spectral weight in these two little things that come up in the before pumping?
Before pumping, we have this peak.
Yeah,
like
there's some spectral weight over there.
Here.
Yeah, if you do the second derivative analysis, there's already some spectral weight. What is it?
I don't know.
but that's something that puzzles me, for example.
Really?
It tells me that the temperature is much higher than 100K because the repetition rate of the laser is pretty high. That's a lower ref rate?
Section state out is, I think it's a kilohertz system.
I thought it was
If
100.
I remember this correctly.
I think it's 100 kilos, but that's fine.
I think we should not say
I mean,
because he.
exactly.
He doesn't know.
He's not involved.
No, I don't.
The last questions on
Let's take one.
but
If there is any question of
flow,
him,
and then we can have a
But
broader
maybe
discussion.
this is the start of a broader discussion.
Yeah.
yeah, that's the point.
But, because these data are at 100 Kelvin with probes. So my loose understanding of BEC interpretation is that when I look above TC, I still see a very strongly suppressed density of states. I see essentially no single particle excitations. And so it seems to me it should be possible to make a clean statement about whether the existing data at temperatures above TC are consistent with that picture or consistent with a more or less just scattered electrons kind of picture. So what should we be looking at to nail down that question?
Yeah. What should be observed? I mean, what about this one? Sorry, this one? This is a standard photo emission, RPS photo emission.
Right, so we had that discussion, right, that I think Dr. Kang from Rutgers argued and the optics people argued that their data were somewhat inconsistent with that photo emission. Because I would agree with you that the photo emission data at 340 Kelvin by itself is suggestive of a transition which is destroyed by phase fluctuations with the amplitude remaining, which is kind of what you mean by BCS.
Yeah.
And we heard some people say that optics and the tunneling were not so consistent with these data.
Tunneling experience not consistent. Yeah, I think it's quite consistent. Yeah, because you see, we have the nickel spectral rate above Fermi level, because this here should be something like this. And we have the above Fermi level, we have the nickel spectral rate, and below the Fermi level. This is due to the hybridization, so that this includes.
So this is an argument. So I see. So there's two things here. One is where the density of states sits, and the other is the character of that density of states. And so your argument is that the nickel character of the low energy density of states is telling you that there has to be some hybridization even above TC.
Yeah, that is what the previous speaker said, as far as I understand.
Well, that was said for below TC, but now you're saying this is true above TC.
Above TC, yeah, that's fine. Yeah.
That's the.
Sorry. Okay, yeah, anyway, but this is part one about TC.
I think it's a good moment to thank all the speakers and then maybe start.